inspection robot also has a frontal camera view, so as it's advancing through the length of the pipe, you can sort of see what's coming up. And QS Incorporated actually does a couple of different analyses with the FutureScan robot, a first and second tier analysis. And for those who are interested in radars and radar scanning, the sampling rate is 27 picoseconds. All right, so the next technology I'm obviously going to introduce is going to be GPR, since that's the other thing that we use. So the following poll question is going to be, have any of you actually used ground penetrating radar for GPR? All right, that is coming up. Okay. So yes, there's a lot of people that have and a couple that haven't, it seems like. All right, so that's good. For those of you that have not used it, GPR is a lot like FutureScan, in just simply in the fact that it's sort of a separate radar scanning system. The difference is that GPR uses different wavelengths and antenna pulse width durations, and also it's only used from the surface, the ground surface. The specific GPR system that we used in this study was a US radar seeker STR, and it also had the real-time scanning capability. And you can see in the picture there one of the radargrams from one of the tests that we did during this study. All right, so what we'll talk about now is the actual project and what we did as part of the study. So the project site was a site at the intersection of Virginia 116 and Virginia 122 in Burnt Chimney, Virginia. It's a small town southeast of Roanoke. And so at this site, the Virginia Water Authority wanted to install a water pipe. It was an 18-inch casing. And so as they were installing this, we were allowed to install around the pipe a series of sort of target voids that we were going to use both FutureScan and GPR to try to detect and measure. Also during the study, we did a series of roadway elevations, and we monitored those over time. So we did one set of elevations before reaming occurred, one during reaming, one immediately after installation of the pipe, and then one about 4 months after pipe had been installed. All right, so we also did soil analysis at the site, just so that you can see exactly what kind of soil we were working with. We did most of the standard tests, and had a USDS classification of a silty sand. So that lets you know sort of what we're working with. In the actual project, the first step that we did was as they were installing the pipe, in the last 40 feet of the pipe, we installed our target anomalies. So these target anomalies were basically, it was a packaging foam. So think of what you would wrap something breakable in before you send it out in the mail. That's really used. The reason that we could use this foam as a void, it was because it has a dielectric constant than the surrounding soil. And so any sort of radar would be able to pick up that change in dielectric constant. So we actually installed 4 different target voids. The that you see here was my graduate student, and he is installing one of the voids with one that was working on the project. And so here's another picture. It shows you exactly where we installed each one of the voids. Important because it sort of acts as a control. We know we should find voids when we do the scanning. 4 different voids. The first one was the largest. It was a foot in length. It was about 1/4 of an inch thick. two in the middle there that you see were a little smaller. They were each 6 inches in length and both a quarter of an inch in thickness. And then the last void that we installed was the very smallest, and it was 3 inches in length and a half an inch. And you can see from the picture below that after we wrapped this foam around the pipe itself, we loosely covered it with duct tape so that it would stay secure on the pipe itself as it was pulled down into the ground when the pipe was installed. So, as I had mentioned before, the pipe got installed, and so then the next day we came back, and Hughes came with all of their equipment, and they did the FutureScan radar scan. And we also used GPR to try to locate these voids that we installed. And so what this slide shows is basically that future data for that specific region where we installed those foam targets. And a reminder, that was about the last 40 feet. So as you can see from the radargram on top there, located every single one of the targets. They located it in the correct places at the correct distances. The table below that shows the actual lengths and thicknesses of the targets, and then what Hughes estimated those lengths and thicknesses to be where they scanned. And so you can see, for the most part, they were either very, very close or they were right on the money, which was very, very promising to us. The next slide that I'm going to show you are the GPR results for the target region. Unfortunately, the GPR did not work at all. What we suspect happened was that there were already some installed utilities over top but below of the ground surface in the area where the pipe was installed. And so what you see here is at about depth of 2.5 to 3 feet. There was a whole lot of scale. And what the GPR actually picked up were the utilities that were lying over top of the actual pipe. And so some reflections of the waves there did not allow us to see the pipe or any of the target voids that we installed. So that was a little bit disappointing, but also a little bit enlightening. Those were our GPR results. As far as the results for elevations that we had taken before, during, and after pipe installation, these are the results for what had happened during reaming. So if you look, the black line on this chart is the baseline, or basically where the roadway was before any sort of installation took place, any sort of pipe installation that took place. And then the blue line is how those elevations have changed after, during reaming. You should also note that basically each one of these elevations were taken along the full 180 feet of pipe length and across the roadway. So we're getting the entire drill path here. So during reaming, we definitely noticed that there was some heaving occurring. The heaving ranged from 0.3 to about an inch. And one of the reasons for this was also that during reaming we noticed that there was some hydrofracture failure. You can see that from the picture here. So we think probably the heave was definitely due to the drilling fluid that was leaking out and seeping from in between the concrete curb, gutter, and the asphalt. The elevations the day after reaming showed some settlement. So you can see definitely there's some settlement here, and in some places settlement was a little bit more than an inch. If we look at the elevation after 4 months after the pipe was installed, this is what we got. Overall, it showed both settlement and heave. The maximum settlement was about 0.78 inches, and the maximum heave that we measured was about 1.62 inches. And the interesting part about this is that not only did the folks from CUSE use FutureScan to scan for our target voids, but they went ahead and scanned the entire length of the pipe, so it was a full 180 feet. And as they were doing this, not only did they find the targets, which you can see in this upper radargram figure inside that blue box, that's where they found our targets. But they also found this very large, what they called anomalous region, where they suspected that there were also some voids occurring. That's that very large red box you see. And that region was, like I said, it was pretty large, and it was detected between 65 feet and 115 feet south of the North Inlet. And so this region actually aligned fairly well with some of the elevation changes that we saw the day after reaming and at the 4-month mark with some of the settlements and that were noted. If we were to look at a cross-section of this anomalous region, it would look a little bit something like this. And of course, we can only sort of get this information because FutureScan does the 360-degree scan completely around the pipe. So we suspect that that's sort of what that anomalous region looks like. All right, so in conclusion, we found that FutureScan was a very promising technology. We really enjoyed working with CUSE and learning about it. Overall, it did a really good job of first off detecting the anomalies and detecting the sizes of the anomalies that we installed. To us, probably the most impressive part was the fact that it was able to detect that void, or the void thickness, with a fairly good accuracy. It was usually about plus or minus 0.1 inch. And since the thicknesses range from a quarter to a half of an inch, we thought that was pretty impressive. I should mention there are some limitations to the technology as it is currently. The first limitation is that it can't be used in earth piping systems. It also can't be used if the piping system is very wet. It's not exactly waterproof, right? And also, in its current form, it can't be used in piping systems that have less than a 15-inch inner diameter, and that's just a function of the size of the robot itself. But like I said, we definitely thought that FutureScan was a very promising technology, and we can foresee a couple other different things that we could possibly use it for as far as post-construction evaluation. The first of those being using it possibly to evaluate compaction. We actually started a project on this because I actually only told you about one of the sites that we scanned with FutureScan. We actually scanned 2 other sites with the sole purpose of sort of looking at compaction. But we didn't have enough time to talk about that today. Other possible uses would be maybe to evaluate any sort of grouting that might be done for an annual space to make sure we actually are getting out all of the voids. And then obviously we might want to look at it in its use in other trenchless methods besides HDD, so things like jack and bore, pipe jacking, microtunneling. Obviously, we think that it is very promising as far as quality assurance or quality control purposes on projects. And perhaps if we can make it a little more rugged and more waterproof, it might be able to have some good uses in looking at actual boreholes themselves and making sure, evaluating kinks in those boreholes and seeing if the pipe that we're trying to install might be able to fit safely through this borehole. So there are a couple people I would like to acknowledge. A lot of them are actually in the audience, and they're going to help me answer any sort of questions that you guys have. So the first one is going to be Frank Morris, who's my graduate student that did all of the work on this project. So very well, he can answer lots of questions. Also, Ed Hope, who's our partner at Victor, and then Tony Winowich and Tom Jastrzebski, who were the technicians at Hughes that came up from Florida and helped us out with this project and did all the data analysis. And then also Dean Grindstaff and Mike Igo of Grindstaff Underground. We definitely need to thank them since they let us come to their job site and wrap foam around their pipes, and they were very gracious about it. All right, so I should also mention that in the audience we have Arun Jagannathan from Louisiana Tech. And so he is actually the original creator of the FutureScan robot, so if you have any sort of questions about the robot itself, he can definitely answer those. So our last poll question is going to be what you guys think about FutureScan now that you've heard about it. And you seem like it's a promising technology. And after we answer this, I guess we can, Emily, open the floor up for questions?
Yep. I have a yes.
Oh, lots of yeses. That's good.
Okay, well, thank you, Lindsay. I think that was a perfectly timed presentation, so I really enjoyed that. Also, I mean, I think we've learned a lot about FutureScan. If you guys have questions, again, many of the people in the audience are fairly familiar with FutureScan, so I really appreciate Professor Jagannathan and some of these other folks joining us. But for people that, do have questions, with either what specifically Lindsay did or with the technology, because again, we have, many of the people behind the technology here, please type it into the chat box. I think if you speak into your phone, we can also hear you, but may be helpful for all of us if we see your question too. So I like this presentation because, Lindsay told us about, the specifics, and then also, that it, the project was used for protection, right? And part of it, some of these other ideas, do you think it's going to be feasible to make it waterproof enough to go into those boreholes and pre-piped kind of thing? Because that to me almost sounds like the most exciting use of it.
I think that's farther off than using it for some quality control.
Okay.
So,
here's a question from Tom about how long did it take to make a complete pipe scan?
But Tom was there.
So maybe he's planting us that question.
So it took, well, it depended on the pipe rate, right? And sort of the rates that we're going through the pipe. Yeah, so Frank says it was about 15 minutes for each scan. And you also have to remember that we had to rotate the antenna for each run, essentially, right, so that we could scan the entire 360 degrees around the pipe. And Tony says they're already working on more rugged stuff and waterproofing.
Waterproofing, yeah, fantastic. So, 15 minutes to do like 100 yards of, or
so
100 feet of?
It was 180 feet of pipe.
So it's the robot moving slowly, but moving.
Yeah.
So, but that's also that they are working on the rugged antenna. So at the rugged antenna structure, then you wouldn't have to adjust as much. Is that the idea?
So I think they actually are working on making. I think Tony's about to answer it, but okay. I think they are working on making it so they can sort of rotate while they're scanning, so you won't have to do as many runs.
Right.
And then, what's the other question?
So I guess so the 360 antenna.
Yeah, so they now have the 300.
The whole run in one pass.
Yeah, so it'll be in one pass, which saves time.
So how many passes did it take when you guys were doing it?
So we would do it at specific clock angles. So we did it at, let's see if I can remember. It was 12.
Where you need Frank again.
2, 4, 6, 8, and 10, I think. 12, 4, 6, 8, 10. those 6 passes.
6 passes. Awesome. Okay. So yeah, so the 360 sounds a little more exciting than having to do it.
Yeah.
6 times. Oh, we got 2 people typing in answers here, so I appreciate the involvement here. Ooh, an array of 8 antennas. So the 360 antenna is actually an array of 8 antennas to do the entire 360 degrees. Before it was 8 runs of 15 minutes. So between 6 and 8 rounds, I guess, a month out. Wow. So thank you, Tom. That helps a lot with this. So I think we have 1 or 2 more participants, so maybe they're getting ready to to listen to our bridge thing next. So let's see what our next. I like how it tells us somebody's typing here.
Here's somebody typing.
Yeah, you may be able to talk to us, Tom, since we can hear you typing.
Oh, that would be a lot easier. Can you hear me?
Yes.
Yes.
Oh, well, if you can hear me, well, that's good. I was just going to elaborate a little bit on Lindsay's excellent presentation. Like I just typed in, the robot is able to run at about 30 feet per minute. Right now, as far as waterproofing, that sort of thing, the antenna is not really the limitation as far as water in the pipe. The problem with water, scanning wet soils, for example, is that water, for those of you who may not be familiar with GPR and the nature of how radar waves or radar energy propagates, RF energy propagates through materials of different dielectric characteristics. Water happens to be one of those materials, like metal, that we cannot see through. It's that what's called the dielectric permittivity of the material is such that it makes the water basically opaque to the RF energy that impinges upon it, and so it's very difficult to see through soils that have a very, very high water content. The best soils, if we wanted to talk about the best case scenario are soils that are relatively dry, to be able to see through and to be able to see into beyond the outer pipe wall of the pipe that you're scanning around. And in those situations, for dry sand, where the dielectric constant is relatively close to that of air, 1, the depth of penetration could be 2 to 3 feet, perhaps, as either the water content or the clayey characteristic of the soil outside the pipe increases, then the depth of penetration reduces. Under those circumstances, then we have more difficulty seeing out beyond the pipe wall. Actually, these robots themselves are more than capable of being operated submerged in a pipe. The problem, however, is the radar energy just can't pass through can't pass through the water. So just as with the case of, say, wet soil on the outside of the pipe and the inability for the radar energy to scan deeply outside, through the soil through wet soil, we have a similar sort of problem where there's a small amount of water in the pipe. Let's say, for example, the pipe is half full of water. In those scenarios, we can still scan a pipe looking up. We just can't scan a pipe looking down at, say, 6 o'clock. Because the water in the bottom of the pipe would just reflect the RF energy, and we'd be basically looking at essentially an RF mirror. So for those who might be interested to know whether one can scan a pipe that is partially that's partially full of water, the short answer is yes, you can, so long as your antennas are not pointing at the water themselves. So in directions where there's no water, there's no reason why a scan can't be executed. We saw that sort of behavior at the other sites that we did out on Route 635, where those pipes were had water on the bottom of them, and yet we could scan the rest of the pipe.
Right, that was the other site that they scanned, but we didn't talk about today, yeah, where we were sort of looking at compaction. That was a site that we had known that it was very poorly compacted. We wanted to take a look at that using both GPR and the FutureScan.
Great. So, and GPR also has trouble with waters and pipes and the reflections and mirror problems.
I mean,
right?
yeah, it definitely has reflection problems. I mean, that's completely obvious just in the GPR results for this, and that all of the utilities that were above the pipe itself, it reflected those, and we couldn't see anything below those utilities, which is not what we wanted to see at all. So we didn't care about the utilities, but it did fine.
Right, right. And so then Tony's weighed in here that, you know, you can differentiate between a water-filled void and a water-soaked soil. So that sounds like that's helpful. Mm-hmm. So this is all good. So I really appreciate this conversation. Again, if other people have questions, you know, I think please ask them. At this point, I think it would make sense for us to upload the other presentation so that Professor Chase can go ahead and talk to us. We're going to things around so he can talk here. I think at this point, yeah, we do want to ask Professor Chase to talk to us about development of thermoelastic. Sorry, he's going to have to say it better than I can. So, as a practical bridge inspection method. So, thank you, Professor Chase.
Okay, good afternoon. We'll be talking about a project that we're just finishing up after 3 years. The initial portions of the project were funded by MAUTC, and there was a follow-on project that was funded by the Virginia Department of Transportation. I wanted to acknowledge that significant portions of this presentation were contributed by Dr. Adugomfi, who is a postdoc working on this project, and Dr. Paul Fox, who is an instrumentation engineer whose company developed and delivered the field computer and the infrared imaging system that is a part of this system. What I hope to do in the next 25 minutes is to explain why this is an important advance in bridge inspection. I'll introduce what thermoelasticity is, because I suspect most of the audience are not familiar with it. I'll provide an overview of the 3-year project and answer any questions that you might have. Before we do that, though, I wanted to ask, have any of you driven over a highway bridge recently?
We're going to move that poll into place, and I'm going to interrupt and thank Tom and Tony and Professor Jagannathan for all joining us for the conversation. I really appreciate Professor Ivey-Burden and also your guys' participation today. So it looks like we have, many of us have driven over highway bridges recently. So
that's not surprising. I expected most of you to have driven over a highway bridge recently. But one of the things that have led to the collapse of bridges over the years is fatigue and fracture. There are 3 well-known bridge collapses shown in these pictures. The first in the upper left is the Silver Bridge, which happened in 1967 near Christmas time, when 46 people lost their lives as a result of that collapse. The middle image is of the Mianus River Bridge carrying Interstate 95 through Connecticut, which collapsed in 1983. 3 people lost their lives on that collapse. Just as an aside, I happened to have driven over that bridge the day before it collapsed.
Oh.
And the The third image is of the Hone Bridge, which was a large bridge in Milwaukee, Wisconsin, that experienced a brittle fracture. There were 3 girders holding up the bridge. 2 of the girders fractured completely through, and it was only because the 3rd girder did not completely fracture that the bridge did not collapse, but a replacement bridge had to be built at a cost of several hundred million dollars. So fatigue and fracture is a significant concern and is something that bridge inspectors spend a lot of time trying to detect on bridges. The current practice for detecting fatigue cracks on bridges is to rely on hands-on visual inspection, which means that we have to place an inspector within arm's length of the detail that he's trying to inspect to determine if there is a crack there or not. As you can imagine, this is quite tedious. Because of the time and effort required, it is very expensive. It is dangerous for the inspectors on many locations where they're hundreds of feet in the air, or they're in a work environment where there are high-speed traffic that they have to contend with. And unfortunately, visual inspection is not particularly reliable in being able to detect fatigue cracks. There's a need to improve the ability to detect fatigue cracks on highway bridges. Also, another important aspect of the current practice is that you have to wait until a crack has already formed in order for you to identify that there's a problem. So we proposed a technology development project to try to deal with these issues. But before I describe the project, I wanted to know if any of you were concerned about driving over those bridges that you indicated you drove over recently.
Oh, Jim will give us the poll here.
And most people don't give a second thought to the safety of the bridge that they go over. They take it for granted that that bridge is safe and that the owners of the bridge are doing whatever is necessary in order to make sure that the bridge is safe and won't collapse. And from firsthand experience that the owners of these bridges, usually the state departments of transportation, take this responsibility very seriously and expend a lot of energy trying to make sure that they detect any problems on the bridges, but the current inspection methods are less than what they really need to be. So the purpose of the project that we embarked upon was to develop a device that would automate the detection and monitoring of fatigue cracks on steel bridges by imaging the dynamic stress concentrations at fatigue-prone details. We wanted to identify and quantify the precursors to fatigue cracks and not wait until the crack had already formed before being able to identify a potential problem. We also wanted to improve the ability to detect existing cracks. And a very important objective of this project was to develop a technology that would allow people to be able to assess if whatever they've done to take care of the problem was effective. The current practice is to do a retrofit, and the only way you know if it worked was to see if the crack stopped growing or if a new crack formed. So having the ability to assess whether or not what you've done is effective is an important contribution of this project. So what is the thermoelastic effect? If you take a solid, a volume of a solid, and it's at a certain temperature, so there's a certain amount of internal energy in that volume of solid. And if that volume were to be expanded, the amount of energy remains the same. So in fact, when you expand a solid, its temperature goes down a little bit. And when you compress a solid, you're forcing that amount of energy into a smaller volume. And temperature is really kind of a measure of energy intensity. So the temperature goes up a bit. Now, these changes in temperature are very, very small, and most people don't even know they exist. But we're making use of this effect to actually be able to detect what's happening on a detail that's subjected to varying stress levels. The equation that describes the relationship between the change in stress and the change in temperature is given here. I'm not going to go into detail, but essentially the amount of the change in temperature is a function of the material. It's a function of the ambient temperature, and it's a function of how much the stress is changing. And also, whatever heat is generated, if the temperature goes up, that heat will tend to move away from that site. So that last term can be significant, and we have to deal with that. The second term, that the Q over rho C term, is the term that describes the heat that can be conducted away. And if the change in stress and the change in temperature happen quickly enough, we can neglect that term, which makes the thermoelastic method easier to implement. And fortunately, most of the loading events that occur on a bridge, which are due to traffic, occur fast enough so that we can neglect the flow of heat away from the detail. The thermoelastic signal, the change in temperature, essentially can be simplified to constant, some thermoelastic constant, which is a function of the material, and the ambient temperature, and the change in the principal stresses. So as a detail is loaded, the principal stresses change, and there's a change in temperature that takes place. The magnitude of the change in temperature is quite low. For typical stress changes on bridges, the amount of temperature change is well below 1/100th of a degree. So we have to develop a technology that can be sensitive enough to detect those changes. The project that we are describing involved a number of tasks, a significant amount of work with the computer, both in the laboratory and eventually deployed in the field. We'll quickly go over some of the highlights of the work that was done. We did an initial project which was funded by MAUTC, which was actually a proof of concept. Up until this project, thermoelastic stress analysis had been used, but more in a factory or laboratory setting. The equipment that had been used was very, very expensive, in the $50,000 to $100,000 range. What we wanted to pursue this project was to see if we could do thermoelastic stress analysis using low-cost infrared cameras that had become available, where the cost of the camera was around $10,000. So the MAUTC project was a proof of concept project that investigated whether or not that was even feasible. We used a specimen, which was a plate with a hole in it, as a test specimen. The stresses that would be created in such a specimen when subjected to a tension load are well known, and we could assess our success or not by looking at whether or not the image that we produced with the low-cost camera looked anything like the theoretical image. The concept is to take infrared images while the specimen is being loaded dynamically, store that information in the computer, and also at the same time collect a reference signal that is correlated with the load that's being applied to the specimen. We then process all of those images that have been collected and only extract out the information that is in those digital files that are correlated with the loading events that should have produced the thermoelastic signal. So if we're successful, we should end up with an image that looks something like what the theoretical image for a hole in a plate should look like. And this was the image that was produced by the proof of concept test and the low cost camera that was produced by the at the end of the proof of concept project funded by MAUTC. With this, we were able to convince the Virginia Department of Transportation that a follow-on project to actually develop this into a fieldable inspection system was something worthwhile, and they did agree to fund us. So before I explain what we did, I wanted to find out whether or not this explanation of the thermoelastic effect was understandable. Good. Very good. So, oh, wait a minute. Okay. Okay. Move on. The follow-on Virginia Center for Transportation Innovation and Research project was to develop the ability to not only extract a thermoelastic signal using a nice sine wave, but to actually do it with the random loading that is characteristic of bridges, to design and develop a complete field system, to test the capabilities and limitations of the system, and to conduct field tests with the system to demonstrate that it works. The laboratory set testing was very similar to what we did during the proof of concept, where we essentially evaluated the ability of the system to extract thermoelastic signals from specimens, but during this phase we loaded the specimens with random loading as opposed to nice sinusoidal loading. Thermal camera we ended up using is a low-cost, uncooled microbolometer camera, which because of the developments being driven primarily by Homeland Security needs, the cost of infrared cameras has come down significantly and continues to fall. So the cameras we can use to implement this technology are well below $10,000. We also had to develop a special computer interface with the cameras, also collect information on the bridge, stored in a computer, be able to hold on a bridge and left unattended for a significant period of time. The significant effort went into developing the ability to detect a loading event, but also collect data that was happening before the loading event was detected. So we have to be continuously collecting data from the bridge, detect when a load event occurs, go back and retrieve some of the data that occurred before the loading event, store some of the data after the loading event, and all of that information is needed in order to extract the thermoelastic signal from the data that's acquired. In order to extract these very low signals from very high noise environments, we had to rely upon a special signal processing method called lock-in signal processing, where we used correlation technology or correlation signal processing to only extract information from a very noisy signal that is correlated with the loading event that produced the thermoelastic signal that's buried in that noise. And we were successful in implementing this lock-in post-processing method and capability so that we were able to extract a thermoelastic signal from a randomly loaded specimen. Just looking at the raw thermal image, it's nothing but noise, but once we post-process that information with the lock-in thermography, we're able to extract out the thermoelastic signal that was buried in the thermal noise from the raw image. Using this capability, we tested our ability to detect a fatigue crack based upon the fact that if a crack is present and it is being subjected to a dynamic loading, the stress at the tip of that crack is very high and is producing a thermoelastic signal that our system can detect. So you can go out with this system and take images and determine whether or not a fatigue exists and whether or not the fatigue crack is experiencing sufficient stress to be in a growing state. The field test that we did on this project was conducted on this bridge carrying Interstate 64 over the Maury River just outside of Lexington, Virginia. It's a large bridge which has a history of significant fatigue cracking in it. The goals of the field test were to deploy the system for an extended period of time. The system has been designed to be battery powered. We've acquired the data triggered by multiple truck events and extracted stress concentration information from the data that we collected associated with random truck loading on that bridge. The field computer is shown installed by clamping it to the girder. It is connected to the infrared camera, which is aimed at a detail that is subjected to, or we suspect has large stress concentrations in it when a truck goes by. There's also a strain gauge attached to the bridge that measures when a truck happens. And what you see here is the first ever image collected from a bridge with a fieldable thermoelastic stress analysis system demonstrating that we are able to actually identify, detect, and quantify the stress concentration at a fatigue-prone detail due to random truck loading. So, do you think that this system is a valuable addition to bridge inspection and its ability to detect fatigue cracks? We agree. thank you. We have demonstrated that we have developed and are to be delivering this system to the Virginia Department of Transportation at the end of this month. We have validated its ability to detect fatigue cracks and measure stress concentrations in the laboratory and in the field. We do plan to try to interest other DOTs and bridge owners in this technology, but this technology is also applicable to any dynamically loaded structure, particularly structures made out of metal because they have a very strong thermoelastic signal, but also because they're prone to fatigue. I want to acknowledge the support and contributions by the Virginia Center for Transportation Innovation and Research. Certainly, we could not have done this project without the proof of concept study that MAUTC funded. Fox Consulting delivered a system that can be duplicated, and certainly the support from the University of Virginia is greatly appreciated. So I'd be happy to answer any questions that you might have. I know that was a lot of information to digest in a short period of time.
No, that was great, and again, you guys are doing awesome with timing, so please type in your questions. It looks like somebody is typing in here. Here we go. How long does the signal processing of an image take? That's a good question.
Okay, the lock-in thermography actually processes as many images as we can collect. So on the field test, we collected 51 events in 1 hour. That bridge is a lot of truck traffic. We post-processed 10 about 1 hour. We post-processed all of the images overnight, and the post-processing is done separately from the data acquisition and on a separate computer that has the post-processing software on it.
So my question is, how far away from the fatigue area should the camera be?
We're using a camera which has a fixed focus, and the focal length is about 30 inches.
Right, so slightly more than arm's length.
Yeah.
But...
And, well, that's a function of the lens.
Mm-hmm.
Also, for that bridge, the bridge that was tested, there were actually 2 fatigue cracks in the region that they were interested in having us perform this test. So they wanted us to locate the camera in such a way that we were actually looking at 2 fatigue cracks at the same time.
Yeah, that was my question, is whether you can use one camera for multiple...
If they're close enough together.
If they're close enough. And so in this case, you had a hint on where these fatigue cracks were?
Yeah, we usually have, well, one, because if the crack's already there, we know where the problem is. Also, from experiences on other bridges with similar details, we know where it's likely that fatigue cracks are likely to form. And on this particular bridge, there are many locations which have cracks on them. So we picked one that was most interesting to the Virginia Department of Transportation.
And so with your testing system, you're able to see whether the cracks get bigger, like in sort of...
Well, we can measure the dynamic stresses and the high levels of stress happening at a particular location. So the level of stress we're able to image is the higher the stress, the stronger the amount of temperature change, the more radiation comes off of the surface, so the stronger the signal is that the camera picks up. So For steel surfaces, we can reliably detect stress ranges that are greater than 10,000 pounds per square inch. And for steel, which has a yield strength usually around 35 to 40,000 pounds per square inch, it's usually very high stress levels near that yield strength that result in fatigue cracks. So we design the system to be most sensitive to high levels of stress.
Cool. So we have another question here. Longer term, is there a plan to place the cameras on moving platforms to allow more comprehensive data collection? I like that.
Like robots or something?
Well, yeah. Like I mean, because we've heard of bridge inspection robots, right?
Yes. There are bridge inspection robots, which have like are sort of magnetic crawlers that attach themselves to the steel and can be moved from one location to another. Highway bridges are very difficult, this type of technology to be used because of all of the obstructions that the robots have to encounter. There are stiffeners everywhere. There are varying thicknesses of materials. There are splices. There are joints. So it would not be likely that we would simply strap this system onto a existing magnetic wheel robot and deploy it on a bridge. But there are plans to develop inspection robots that can accommodate all of the difficulties that are associated with bridge inspection. And once those platforms are available, this technology plus other non-destructive evaluation technology could be deployed that way.
That sounds good. Here's another follow-on to that. I've heard of proposals to place cameras on moving quadcopters to do inspections from off the bridge. So they would fly.
I even have one.
Wow. Yeah, we'll definitely
But
see
the quadcopters are small, they're battery powered, they have limited payloads, they have limited flight times, they can be deployed for taking snapshots or videos of some bridges, and there are companies that have actually started doing that on a fee basis. But the infrared, the thermoelastic stress analysis system would have to be reduced in size significantly before it would be possible to deploy it using that technology.
Cool. So, looks like we're getting another follow-on to that. And so quadcopters and UAVs are similar?
Yeah, an unmanned aerial vehicle and a quadcopter, they're both
Analogous?
A quadcopter is like a little helicopter with multiple rotors. That, because it has multiple rotors, it has a bigger payload than a helicopter with one rotor. They're also able to be made much smaller. Usually they are deployed and operated with a remote control system similar to the aircraft. UAVs, on the other hand, tend to be more sophisticated. They, in many cases, they are autonomous. They can perform missions without any human intervention.
Without a remote control.
Yeah.
Okay.
Although it can also be flown with remote controls. Also, they have much further range. They can stay aloft a lot longer. And as the military systems demonstrate can have all kinds of capabilities.
So the UAVs may have larger payloads to accommodate like this bigger camera.
Yeah, but
and
they
stuff.
don't, they are not stationary. They are not able to hover.
Oh, to hover and do it. That's the difference. Okay. So here's another question of how long does it take to actually take a picture? 3 frames per second, so just a second or two to collect data at specific locations for later analysis.
Right. We trigger off of load events that are detected with a strain gauge. We have the ability to specify how much time we want to acquire data for each. We set up a pre- and post-trigger time period. For the testing that we did on the bridge that I showed you, we had a 1 second pre-trigger and a 6 second post-trigger. So the actual image is 7 seconds worth of data. That, and we acquired 51 7-second images, which at 30 frames per second is 210 frames for each one of those events. So we had a whole bunch of frames to deal with.
Well, that's what you used in your post-processing,
Right.
and that's what took 6 minutes per 7-minute setters, whatever
Right.
you gave us. So that makes sense. So I've enjoyed this discussion. I think if we have questions that are now burning for either Professor Ivey-Burden or Professor Chase, I think now's the time to bring them up. I really appreciate everybody. I know it's a small group, but it sounds like we've had a few questions and interaction here. So I appreciate everybody listening into this. And again, we do have the 3 more webinars coming. I think now may be a good time to put up some questions, sort of a short evaluation. I guess we have. Yeah, unfortunately, we only have the please rate instructors' subject knowledge and communication skills. We only have 2 people presenting today, and I'm sorry I didn't check or change that. We do have the information for the next webinar here, October 9th. And again, if somebody has a question, I think most of the people can speak into their phone. And so while we get a couple responses here, I really appreciate everybody's participation today, and please speak up if you do have another or want to continue the conversation. So, yeah, Lindsay, Steve, you guys have some parting remarks?
We're hoping to, it's actually the first presentation of the field results that you saw. The field testing took place last week.
Oh, awesome.
Last Thursday and Friday.
Wow, well, thank you for getting it together and to present it to us.
And we will certainly be trying to communicate the capabilities of this new technology to as large an audience as we're able to. And we think that it could be very useful to help improve the safety of highway bridges and to improve the ability to detect and manage any fatigue cracks that exist. So we're interested in talking to anybody who might be interested in trying to help us deliver this technology to a larger market.
That sounds great. So again, I appreciate everybody's time and participation today, and I think we're getting some good feedback on our questions here. If you have some things to type in, we definitely try to pay attention. It looks like somebody does say they want to understand the direction of this type of work, so that sounds promising for what we're doing, both FutureScan technologies and the thermoelastic stress imaging. So I appreciate our instructors today, and I definitely appreciate our FutureScan guys for joining in and answering questions and asking questions. So, yeah. So I think this is all very positive. So And I think we did start a recording of this. It will be available on our website. Again, you can email any of us, and we can try to get you more information, and that will also help Professor Chase with his dissemination of these results. So thank you, everybody, and yeah, please tell us if you have anything now and in the future. So thank you.
Thank you.
Thank you.